Okay, so in the last class, we discussed about floating point and fixed point data representation. So, fixed point means the decimal point is fixed. We cannot shift the data right or left from the decimal point. So the digits are fixed in a fixed point number, and suppose if the range is if the data is more, then that format is not suitable in a computer data representation. So for that we go for the floating point data representation, and in floating point data representation we can shift the decimal point, and any large number we can represent in a small form by shifting the decimal point. So floating point data representation. So in the last class, we discussed one example. In the last class, we discussed one example. So the same example I will explain once again. So floating point means what? You have to shift the decimal point and you have to make a large number into a small form. So this is the number 0.254 into 10 raised to 3. Okay, 0.254 into 10 raised to 3. Represent this number in a normalized base 8. Normalized base 8. Now here 10 raised to 3 means what? It is a base 10 form. Normalized base 8 floating point format with a sign bit followed by a 3-bit excess 4 exponent. Excess 4 means you need to add 4. You need to add 4. Excess 4 exponent followed by 4 base 8 digits. 4 base 8 octal, that is Mantis apart. 4 base 8 digits. So this is the number. So here simple thing is there. You have to convert the decimal number into octal form. You have to convert the number in a octal form. 0.254 into 10 raised to 3. This is the base 10 form, the given number that you have to convert into the 0.254 into 10 raised to 3. It's a base 10 means decimal number they are given, that you have to convert into it is equivalent to what? 254 into 10 raised to 3 is there. So 0.2, so it is equivalent to this number 254. So this is your original number, base 10. So this you have to convert into what? Octal form. You have to convert into base 8 form. Okay. So you have to convert the target base. What is the target base? Base 8. Base 8. So this is the number 0.254 into 10 raised to 3. So that is equivalent to 254 base 10. So using the remainder method, so octal means you have to divide by 8. So here you will get 376. Okay. So 376. So you're representing in this form. So these both are equal. There is no difference. Okay. Normalization means what? 376. Okay. Into 10 raised to 8 raised to 0 base 8. So there is no difference here. So normalization means you are shifting some decimal point. So here 0.7 into 8 raised to 3, there is no difference. यहाँ हमने किया था ना 0.254 into 10 raised to, that is equivalent to 254. So same. Okay. So there is no difference. So this is your exponent value you will get. Okay, why this why we represent the number in a normalization we'll discuss in the next slide. So here we are getting an exponent 3. This is the mantissa part. Okay, so what happens here? Hmm, sign this number is a positive, so sign is 0. And exponent, what they are given the condition, 3-bit excess 4 component. Excess 4 means we need to add plus 4 to this exponent. What is the exponent? 3. 3 plus 4. So what is the value? 7. Exponent value is 7. Okay, so this is the exponent, 7 binary. And and the mantissa part, this one, 376. So you have to make it to 4 digit. So how? By adding the 0.3760. Okay, and the binary of that. So this is the how the computer understands. So you have to convert this number base 8, base 10 to this form. Okay, this is in octal form. Okay, so in this way we have to represent the number. uh, so one more example. Convert conversion example. So convert this 9.375 into 10 raised to 2. Okay, 10 raised to minus 2 is there. It is a base 10 to base 2 scientific notation. Means decimal to binary conversion. In the previous example was base 10 to base 8. Okay, right? So here we are converting base 10 to base 2, base 2 binary form. Start by converting from the base 10 floating point to the base. Okay, so for this, the given number, so what we have to do, 9.375, okay, into 10 raised to minus 2 is there. Okay, so this number we have to convert. Here decimal point is there. Okay, right? So 9.375. So normally how you convert the number into binary form? For example, if suppose if there is an integer 91, so 91 to the base 10, how you convert into binary? By which method? So that is by division method, by remainder method. Okay, by remainder method, you will divide 91 by 2, then you will take the remainder. Then suppose if it is 0.25, 0.25, which method you use? Multiplication method. Okay, 0.25 into 0.25. So for this number, how you find the binary? Which method? Multiplication method you use. Multiplication method we use for the conversion of binary. So here you need to convert this number 9.375 into 10 raised to minus 2 in a normalized form, in a fixed point format. So that is, you have to shift this minus 2 is there. Minus 2 means what? You have to shift the decimal point to the left side. 0.09. Two digits you have to shift. 0.09375. So this is the equivalent number. Equivalent number of this 0.09375. So it is a base 10. It is a base 10 form. Okay, this is a base 10 form. So 0.09375 into 2. It is a base 10 form. So 0.09375. So here we have to use multiplication method. So here after multiplying we're getting 0.1875, and again you have to take this fraction part. Okay, the fraction part, then into 2. Okay, again you are getting the 0.375. So again you are taking the fraction part into 2. Okay, then 0.75 into 2, 1.5. So here again you have to take fraction part. What is the fraction? 0.5. 0.5 into 2, and this will be repeat. Okay, so you have to stop the process. You have to stop the conversion of binary. Okay, then so for this particular base 10, what is the, so here you have to take from top to bottom. 0 for this number, the 0, here you will get 0, and here 1 1. So 3011. This is decimal and binary. So finally convert. So now we got the in a base 2 form. Okay, convert to normalized base 2 floating point. Base 2 floating point. So you have floating point means you have to shift to base 2 floating point, means you have to represent the number in a normalized form. So normalized means here the decimal point you have to shift to the right side. So this number, this number we can write it as 1.1 into base is 2. So here we are shifted 1, 2, 3, 4. 4 digits we are shifted to the right. So 2 raised to minus 4. This is the normal form. Okay, so you should know this conversion. Then only you can represent the IEEE standard of data representation. How to convert the one base to another base conversion. Okay, the decimal to octal or decimal to binary. So normalized means what? Like some number, for example, normalization means like okay, so this is the one number. So this number you have to represent in a normalization means this bit you have to shift to the left, one of the, means you should get 1 in the leftmost bit. So 1.101, means there should be a 1 at the leftmost bit. Okay, so how many bits we have shifted? 1 2 3 4 5 into 2 raised to minus 5. So this is normalized form. Normalization. So I'll tell you why it is important, normalization. Because for in IEEE data representation, we have to represent a sign, exponent. Exponent part is very important. This part, sign, exponent, and mantissa. Okay. So with this, I want to know from your side: is there any doubt in representing in conversion of number from decimal to binary, decimal to octal? Yes, anyone? You just mention in the chat so that I will discuss once again the same problem. You mention in the chat that, or you can speak directly if you have any doubt or if you are not understood the concept. Because for IEEE data representation, it is very important. Okay, IEEE data representation. Shall I go ahead or say anyone else? If you're having any doubt, mention it. Otherwise, we'll move forward. So IEEE data representation. The IEEE standard, the 754 floating point. The standard addressed many problems found in the diverse floating point implementations that made them difficult to use reliably and reduce their portability. So IEEE 754 floating point is the most common representation today for real numbers on computers, real numbers on the computers, including the Intel-based PCs, Intel-based PCs, Macs, uh, most Unix platform. So they use the IEEE 754 standard data representation. IEEE 754 data representation, and there are two types. So it is very important in your exam. Definitely, you will get a question. IEEE 754 floating point for formats. So the first type is single precision data type. The second type is double precision data type. Double precision floating point number representation. The first is single precision, second is double precision. So single precision is a 32-bit format. Single precision is a 32-bit format. Double precision is a 64-bit format. 64-bit format. We will discuss some of the examples. You have to represent the number. You have to represent given any number in a particular format, single precision or double precision. So single precision, double precision. In a single precision, the one bit is reserved for the sign bit. Here one bit is reserved for the sign bit. 8 bit are reserved for exponent. 23 bits for the fraction. 1 bit for the sign bit. 8 bit for the exponent. 23 bit for the fraction. So total how many bits? 32-bit data representation. 32-bit. It's a single precision data representation. So in similar to that in double precision, in double precision, one bit for sign, 11 bits for exponent value. So exponent value and 52 bits reserved for the fraction part. So how many total? 64-bit representation, 64-bit fraction. Okay, so that is about the single precision and double precision data representation. Single precision and double precision data representation. For single precision, how many bits single precision? 32-bit data representation. So in 32-bit data representation, sign, exponent, sign, exponent value, then fraction. Sign, exponent, and fraction. So for single precision, sign bit 1, how many bit exponent? 8 bit exponent, 23-bit fraction. So total how many bits? 32 bit for the single precision representation. Then for double precision, for double precision data representation, 1 bit for the sign, then 11 bit for the exponent, 52 bit for the fraction. So 52, 53, 63, 64. Okay. 64 bit data representation. Sign bit, exponent, and fraction. Means you have to represent the number. You have to represent the number in either single precision format or double precision format. So that is your floating point IEEE 754 data representation. So there are some important things here. So now I want to know from Abhishek. Abhishek Gowli. Can you hear me, Abhishek Gowli?
Yes, sir.
So how many types are there in IEEE 754? How many types of data representation? Yes, Abhishek Gowli. Yes,
Just a minute, sir.
Madhuri.
Yes, sir.
How many type of data representation?
So two types, single precision and double precision.
Okay, single precision, how many bit?
So it's totally 32 bit, in which 8 bits are for exponent, a sign bit, and 32 bits are for fraction.
Okay. Okay. Then so there are several ways to represent the floating point numbers, but IEEE 754 is the most efficient in the most cases, most efficient. Okay. So it has a sign of Mantissa sign. What is the sign? Sign means 0 represents a positive number while 1 represents a negative number. So sign means what? 0 or 1. Okay. Okay. Uh, so in IEEE, so sign of the Mantissa. So sign means either 0 or 1. The biased exponent. So this is very important while converting the number to single precision or double precision. In the biased exponent, the exponent field that needs to represent both positive and negative exponents, the bias is added. Bias is added to the actual exponent. So this is very important point. So while converting the decimal number to the single precision or double precision, we need to add a bias to exponent value. Suppose this is the number. Uh, Sorry, it's a binary number. Okay, one 1.001 into suppose 2 raised to minus 4. So what is the exponent value here? Minus 4. So for this, for single precision, we need to add 127 number. So what is the value result? 123. So this number we have to represent in a single precision exponent value. The bias value we need to add. This is for the single precision. Suppose if we represent this number in a double precision, then the bias value will be 1023. 1023 for the 64-bit double precision. So what is the value? So 1019. So you have means for any value, for any exponent, any value, we need to add the bias to the exponent, biased exponent. The bias exponent means for single precision you need to add 127, and for double precision you need to add 1023. Okay, so that we'll discuss. Okay, biased exponent and normalized Mantissa value. The Mantissa is a part of the number in a scientific notation or floating point number that consisting of its significant digits. Here we have to only two digits, either 0 or 1. So normalized Mantissa is the one with only one to the left of the decimal. So the normalized means like this 1.1001. Okay, means one digit at the left. So this is the normalization of the Mantissa. So is it clear? This biased is very important. Biased means you need to add the 127 for single precision and 1023 for the 1023 for 64 double precision. So here the biased value for single precision, for this single precision, what is the bias value? For biased exponent is 127. You are required to add 127 to the value, the exponent value, and in case of double precision you are required to add 1023 value, 1023 to the value. Okay, so the size is 8-bit, that biased exponent size is 11-bit. Here means it's a 31st bit, means if for like 31st bit, here 0 to 22, means single precision is 32-bit, double precision is a 64-bit. So from LSB, if we consider, so here the 0th bit will start, and here 31st bit, 31st bit. So similar to for double precision, 0 to 63rd bit. Okay. So the main thing is that for single precision, in the biased exponent, biased exponent you need to add 127 to the exponent value, and for double precision, how much value you have to add? Plus 1023 to the exponent for double precision. Okay, and what is the size of exponent? 8-bit. 8-bit is the size of exponent. Here 11-bit. 11-bit is the size of exponent. I hope it is clear. The biased exponent. Biased exponent. So these are some of the examples. These are some of the examples of IEEE 754 examples. In the next class, we'll discuss about how to convert that. Okay. So today we discussed how we can convert a decimal number into this type of binary form. Okay, we have converted today. Like for example, yeah, this one 9.37.2 10 raised to minus 2. You have to convert it to binary form. So what is the binary form? This one. So this such a type of the conversion, you know. So, but the thing is that you have to represent in a IEEE 754 format. Okay. So here, what to do? So this is the value. Just carefully, you just listen. Plus 1.101 into 2 raised to 5. So this binary number, what is the exponent value? 5.1 plus 1.101 into 2 raised to 5. So in single precision, what is the size of the bit? Single precision is 32 bit. So what is the sign here? Plus. Plus indicate what is the sign? 1 bit. 1 bit is reserved for the sign. So 0. 0 indicates what? Positive number. Then exponent. So exponent. What is the value of exponent? 5. So in 5 is the exponent value. So for biased exponent means how much value you have to add? 127. So how much now? Value 132. So what is the binary for 132? 132 binary. 2 6 the 12. 1 2 6 the 12. Then 2 3 3 the 0. 2 2 1 the 2 6 the 12. Remainder 1. 2 8 the. Then 2 4 the. Then 2 2 the. Then 2 1 the 2 0. So what is the binary now? So just calculate here. 1. How many zeros are the 1, 2, 3, 4? 1, 2, 3, 4. Okay. Then 1, 0, 0. So how many bit total? Just check it out whether both are same or not. 1, 4 times 0, 1, 0, 0. So biased exponent is very important. So you have to add for the exponent value. How much you have to add? Plus 127. So this is your exponent. Then the fraction part. So what is the fraction part? 101. So here 101. Okay, fraction part 101. And after that, so fraction means how many bit? It's a 23. 23. 1 plus 8 bit for sign. So 23. 23 bit for the fraction Mantissa part for in single precision. So now 3 bit we have. So remaining 20 bit, 4 into 5, 20, 4 into 5. So 20 zeros you have to mention to make it a 32 bit. So we understand this value plus 1.101 into 2 raised to 5. Human being can understand, but in the computer, in the data representation, IEEE 75754 representation. So this is the data. Okay, total 32 bit. 0 is 8 bit, 23 bit. So for this number is equivalent to their corresponding IEEE 7.754 representation is this one. I hope it is clear for you. In the coming next tomorrow class, you just go through you just note down this one problem statement. Just all of you just take a screenshot. Take a screenshot and the B value. The B is there, no? B and C. The B and C, you have to you have to convert the number into the IEEE 754 format. So in this way you have to do. For exponent, you have to add you have to convert the number into single precision format. So you have to add the biased exponent. So what is the biased exponent? 123, 127 you have to add. Okay. Just take a screenshot. Uh, yeah.